Game. So, good morning, class. So, today we'll be discussing magnetic induction. Basically, this is a review of our Physics 13, which we have done several terms ago. Okay, now, so here, we are to consider getting the magnetic field and the magnetic force, where in our system, we only have two moving charges, Q1 and Q. Considering that Q1 is at the origin, and Q is at distance r from the origin. Charge Q1 is moving with velocity v1, and charge Q is moving with velocity v. Okay, now, for two charges moving with velocities v and v1, the magnetic force acting on Q by the charge Q1 would be given by Fm. It is given by mu naught over 4 pi times Q1 over r squared, v cross product with v1 cross product with r over r. Now, take note that mu naught over 4 pi is equal to 1 times 10 to the minus 7 Newton second squared over Coulomb squared. Okay, so from this form, we can rewrite this in equation 2 given by QV cross V1. Now, this is a familiar equation for us way back Physics 13, wherein we're saying that the magnetic force is actually coming from the interaction between the charge and the magnetic field produced by the other charge, wherein V1 is equal to mu naught over 4 pi Q1 over r squared, V1 cross r over r. So clearly, the magnetic field is not coming from charge Q. It is produced by charge Q1 because it is only dependent on Q1. But the force or that field is acting on our charge Q, and for that it becomes a force on charge Q. Alright? So now, to further characterize and compare the difference between field and force, let us consider this paragraph here. So notice that from equation 3, clearly we can see that the magnetic field felt by charge Q on its location does not depend on itself. Rather, it is dependent on another charge Q1. Thus, Q serves as the test charge. It only feels the magnetic field, but it is not the one that produces the field. And Q1 is our source charge. It is the one that produces the field that is felt by charge Q. Okay, now, what if we consider the other case? It is now the force acting on Q1 that we need to get, and the force Fm1 would be following the form equation from equation 1, which is given as this. So mu naught over 4 pi Q1 over r squared, cross product of V1 with V and r over r. So now, from this form, we can now rewrite the force given as equation 6 to be equal to Q1 V1 cross V, where the magnetic field V here is the magnetic field produced by charge Q given as equation 5. So it's mu naught over 4 pi Q over r squared, V cross product with negative r over r, wherein the negative sign here means that it is in the opposite direction, pointing from Q to Q1. Opposite with regards to our previous vector in equation 1, which is taken to be positive, pointing from Q1 to Q. Alright? So clearly we can see that indeed magnetic force is the interaction of the field produced by one charge on the other charge. Okay? Now, if there are other charges present in the region that causes magnetic field on the location of our charge Q, then we need to get the summation of all magnetic fields, which is following the superposition principle. And the equation is given as equation 7, which is the sum of mu naught over 4 pi Qi cross product of V1, Vi with unit vector r over r1, ri squared. Now, we can also show that magnetic force is indeed a action-reaction force. We can show that using equations 1 to 6. So if we use equation 1 for Fm, we can rewrite this in this form. Also, if we are to use equation 4 for Fm1, we can now rewrite it in this form. And clearly, if we compare that, or compare them, we can see that the force acting on charge Q and the force acting on charge Q1 are actually equal in terms of magnitude, but opposite in terms of direction, as shown in negative side. Thank you. Okay, so again, let us continue our discussion with magnetic induction with Lorentz force. If both electric and magnetic fields are present in the region of space, wherein our charge Q is present, then the total force acting on charge Q would be both given by electric force and magnetic forces. So here, E1 is the electric field, and B1 is magnetic field produced by some other charge or just distributions aside from our test charge Q. And equation 9 is giving us the equation for Lorentz force. Now, using equation 9, we can now construct a velocity or mass selector. The idea is this. Consider we have a chamber wherein both electric field and magnetic field are present. So here the magnetic field is assumed to be uniform and directed into the page, wherein the electric field is coming from your parallel plate capacitor from the positive plate towards the negative plate. Once your charge Q with velocity V enters the chamber, then it will feel both electric and magnetic fields. The electric field would be to the left since the charge will be pushed away from the positive charge towards the negative charge. Now, for the magnetic force, we can now use the cross product of V and B to get its direction. And using the cross product between V and B, we can verify that it is to the right. Now, we can now write equation 9 in this form, wherein the Lorentz force is given to be equal to Q times minus E plus VB sine theta. The negative sign for E indicates it is to the left, while the positive sign for VB sine theta means it is to the right. Now, if F is equal to 0, that case happens when E is equal to VB. Now, what's the meaning of that? The meaning of that is the charge will experience no net force. The net force will just be equal to 0. And it will simply pass through the chamber undeflected. It will not go neither to the left or to the right. Now, what is the point? That happens when the velocity is equal to the ratio of the electric field and magnetic field, E over B. So that's a special case. We can use this idea to construct a velocity or mass selector. Okay, now, to continue our discussion, we will extend our discussion on magnetic induction on a current carrying conductor. Let us consider a wire element DL having current I. Then DL is parallel to the direct velocity of the charge carriers, V. If there are N charges per unit volume, then the magnetic force on wire element DL can be written as equation 1, wherein dq can be written as NADLQ, where A is the cross-sectional area of our wire conductor and Q is the dominant charges of our charge carriers. Then next, we can now use this equation for dq back to equation 1. Hence, we have dF is equal to I dl cross B, and then F is simply the integral of I dl cross B over the entire length of the wire, equation 2. Now here, for a closed loop, we can revise or modify equation 2 into equation 3. Okay, now, if I and B are considered to be constants or not functions of the loop, then we can now take out I and B outside of our integration. Then simply integrate dn over the entire loop. But since it is a closed loop, then the integral will just be equal to 0. Now, what is the point? The point is, for a closed loop wherein I and B are constants, there is no magnetic force acting on the wire element or on the circuit itself. Okay. Good afternoon. So today we'll be discussing how to get the magnetic field produced by a magnetized material. To start with, recall that from equation 1, we have obtained an expression for the vector potential A at some distance R2 from the origin, where it is given by mu naught over 4 pi. Then M here is for the magnetic dipole moment, cross product with unit R2 over R2 cube. Okay, then recall that the magnetization, the magnetic dipole moment is related to the magnetization and the volume. So here, we are to get a small infinitesimal element inside your magnetic material, and here we can now apply this notation that the magnetic dipole moment contained on that volume is simply the magnetization divided by the volume. Now, using this identity here back to equation 1, then we can now have the equation for the vector potential in integral form. And then we can now substitute M and the volume here, it becomes this one. Then after that, recall that the gradient of 1 over R minus R prime is equal to this term here, so that we can now insert this term back to our previous equation here, and we can now make this in this form. Okay, then we will use this identity that del cross a scalar function phi times a vector f will give us this function here. Also, the divergence of del cross f can be written as a closed surface integral given in this form. Now, using these two back to our equation for the vector potential, then we have the following. So here we are just simplifying the terms. Then eventually we'll end up having this term. Here we have converted the second term of our equation into a surface integral using divergence theorem. Okay, now define that Jm, capital Jm, is equal to del prime cross m, which is defined to be the volume magnetization current density, and small jm is for the surface magnetization current density, defined as follows. Now, using these two identities back to our equation in the vector potential, so we can now have equation 1 here. Okay, so here we are able to rewrite the vector potential in the form of the current densities capital Jm and small jm. Now, to get the magnetic field, recall that magnetic field is the cross product of del with a vector potential A. So using the equation previously for the vector potential, we can now apply the following identities. Del cross F del G, wherein F is defined to be the magnetization M, and G is equal to R minus R prime by its magnitude cube. Then we can now rewrite magnetic field in this form. Now recall that the divergence of del with R minus R prime over R minus R prime cube is giving us an identity that is related to a Dirac delta function. And furthermore, we have the second identity here. So we can now insert these two back to our equation to M to have the following equations for B. Then, simplifying it here, we have this equation wherein phi m, remember, is the magnetic scalar potential phi m given in this form. So here we are able to get or obtain expression for the magnetic field for a magnetized material. Thank you. Yun lang.